Hi guys, welcome to Learn Electronics Repair, and we have another one of these, yeah. So this one belongs to Elvis. Some people think Elvis is dead, but we see him around here regularly in restaurants and bars singing away, yeah, all shook up and that sort of thing. So Elvis is alive and kicking, and he brought this in. So we've seen a lot of these things before, but this one actually is in nice condition. All the sliders work, they're not sticky. Yeah, it looks pretty clean, to be quite honest, yeah, compared to some. And he says it's stuck in protect mode, okay? And then he said, oh, that's usually something, I can't just remember what he said now, but he says it's usually this. And I said, actually, Elvis, it's usually one of 7 things. So having seen these before in the various guises and versions, I must be becoming some sort of expert on these. So the protect circuit in here is all analog, it's not a microcontroller, and it monitors 7 different conditions, okay? Voltage rails, things like the temperature of the transformer and some other things, okay? And if any of those 7 things is out of the spec or the range, it goes into protect. So I told him this. I said it could be one of these 7 things why it's in protect. He says, oh, actually, it could be one of 8 things. I says, what do you mean? He says, well, somebody knocked a gin and tonic over inside it, or it went inside it. So I said, let me just get this right, yeah. You were singing and somebody knocked a gin and tonic over the desk. He says, yeah, that's right. I says, and then it went into protect mode. He says, yeah. So there we go. We know what's happened to this. He did say, however, that the fact it was a gin and tonic is pretty good because it's not acidic like a cola or an orange juice, yeah, or citrus drink. So he thinks G&T is better to be spilt into mixers. I'm not sure. I didn't ask him. I could message him and ask if the drink went in through the top over here or if it was knocked over and went into the back there. Yeah. There is a grill at the front as well, but I'm assuming that Elvis is in front of this. We'll find out. So, okay, that's what's wrong with it. I think, in fairness, I might as well just plug this in and try it. If I'm really, really lucky, maybe the G&T evaporated, as they tend to do here, and it'll just work. What do you guys think? Well, we'll find out. But I will put the current limiter in. So we have the light bulb over in the shadows over there, yeah. Let's just see what this thing does. That came on fairly bright and stayed on fairly bright and nothing seemed to happen. Now, it could be, I'd have to go back to some old videos whether I need to run these things from a higher wattage current limiter, but I didn't generally like the look of that, so we're going to open this up and let's examine what's happened to it. Okay, so this is the amplifier PCB. I don't see anything obvious straight away in the way of damage or even liquid spill. Hello?
Good morning, Richard.
Good morning.
I honestly don't know.
Oh, okay. I can't see any obvious trace of where it might have gone. Like, you know, as in like liquid damage.
Yeah.
So, I mean, it looks like it's drawing more power than it should. I put my current limiter on it. So I think there's something wrong with it, but I don't know. But basically, you don't know where it went into it. That's the top and bottom of it.
When I looked on YouTube with that fault with the protect button, if you got the amplifier laying down in front of you with the amp on the right amp and the left amp, on the left amp, right at the back of that corner, there's 2 fuses, 8-watt fuses. In the back corner. Oh, you mean like I have to take the fans off and the big heatsink cover off and everything to get back there? You mean that? Yeah, probably. Yeah. I can have a look.
I'll power it up without the mixer panel attached and check the voltage rails, and I've no problem working on it. I just thought a bit more information, anything will help, you know. But,
yeah, no, I can't help it anymore because it's not my mixer.
Oh, I thought it was your mixer.
No.
Oh, fair enough. All right, no worries. I'll continue looking at it.
Thank you, mate. Thank you.
Cheers. See you.
Bye-bye.
Right. Okay, so Elvis just called me, actually. I'd messaged him. Slight difference in the story. He doesn't know where the G&T went in because it's not his mixer. It's somebody else's, okay? So he was told that's what happened to it. But he doesn't actually know where it went into it. I don't see any trace in here. And I don't see, at least on this side of the board, any problem here. This is obviously a previous repair. But we find that a lot here, okay? Either a previous repair or some sort of botch done at the factory. So there's no evidence really of any damage to this, I can see at least. He also says he Googled for what is wrong with this protect, and it says there's two little fuses in the back right hand corner of the PCB, and that's what caused it. Yeah, now I happen to know that is not the only thing that could cause it. It could be that, but yeah, there are plenty of other possibilities with these things. I think we'll power this up without the mixer panel attached, and let's see if we can just measure the voltages. I'm going to do this with the current limiter and circuit again, okay? And we have some test points here, which I think gives us access to everything we need, really. So we have minus 15, plus 5, plus 24, plus 15. We have minus VCC, which I think is 82 on these, and plus VCC there as well, okay? We have ground. I did just check if that's connected to like the metal chassis. It doesn't seem to be. That could be because I have this disconnected, which goes to the mixer. That's the ground lead to the mixer. I have a little DuPont lead here. Surprising how useful all these different sort of leads are, you know, so I can just easily put that onto ground, clip it to my black meter probe, and then I have one and three, which is nice. We can see the current limiter in the corner again in the shadows. I'll probably read lower than expected or lower than normal voltages on this because actually changed my mind. I do this often. Yeah. Let's just check for any shorts first. So this is the plus HT. Well, we're probably charging a capacitor, the big capacitors. What's the negative one look like? This is reversed polarity. Charging. Not a short. 5 volts. Capacitor charging. £24 capacitor charging. 15 volts, say, minus 15. Oh. Well, I'm on the wrong polarity. That's the first thing. I will just say that because it's a negative rail. So I'll connect the red lead to ground. Okay, let's try that again. Capacitor charging. Okay. Let's try some voltages. So, because the current limiter is in the circuit, it's going to restrict the voltages we see, but I'd expect to see some voltage on all of the rails, okay? Let's try it. So, minus 15. Minus 2. Plus 5. I went up to about 4, then went down a bit. Plus 24, what do we have here? 9, 8. Yeah, they go, then they start dropping. Plus 15. Oh, that might have a problem on that one. Yeah. Plus 15. Minus VCC. So this should be, I think it's 82 volts. Obviously it's going to read much lower. 14 then starts to drop. And the last one, the positive. Okay. 14 then starts to drop. I think the way this is behaving, like you get a voltage and it starts to drop, makes me think I have a problem on one of the voltage rails. And I'm thinking it's the plus 15. Because that one doesn't really get any voltage, yeah? If we go to the minus 15, that does get a bit. Yeah, I'm thinking towards a problem on the plus 15. Let's pin this down a bit more. So the voltage regulators are down here at the front. Yeah, so this one 7915, this one 7815. Okay, so those are the voltage regulators. We have 2 fuses. We can just check those, but I think they'll be okay because of the way it's behaving. Oh dear. What do we have here? Would you believe it? Come on. Fuse. That's really good, that is, isn't it? Well, I assume it was making contact. Some people should not be allowed to service electronics, don't you think? This is a 2.5 amp fuse, 2.5 L. Okay, that I'm not sure what its current capabilities are, but I'd say more than 2.5. Are you thinking we put a bit of solder with 2 bits of wire and the solder will melt? Guys, what do we face? Oh, okay. Yeah, I'm pretty sure this is the negative fuse. Very nice. Same, 2.5L. So we need 2 fuses. Out of interest now, if I power this up, will the light bulb go dim? What do you think? What do you think? Hey, what do you guys think? I think it might well do. Let's try it, yeah? Okay. It did, and then went a bit brighter again, so yeah. I'm not sure that's what I expected. That's what I got. Right. So the L means low braking capacity. The T is slow below. Yeah. T 2.5 L. Let's see what I have. And this one, is this one even okay? No, it has gone. Well, I have some T 2.5 AL, so they can go in. Now let's see if we can pin this down a little bit further. So if we put the black lead in here, and we go to volts AC, with this meter by the way, if you just repeatedly touch the volts range, you get like frequency, different voltage ranges, AC, DC, volts AC, this is low voltage range. Okay, so that's how we switch them. Now we should expect to see the same voltage on the transformer windings, about 18 volts you would think. Let's have a look. So bulb is on, That's going 4.5. Okay, go on the other one. We switched on again, and I want to see what happens. About the same. So it would appear that the load on the transformer is about the same on both sides. Okay. So where we do seem to have a problem is on the output of these voltage regulators. So this one is the 7915. That means the output on this one is on pin 2. And we see 3.8. Okay. And this one, the output is on pin 3. And we don't see anything again. So that really does tell me there's some problem on the plus 15. There is some possibility this is all red herring. Well, that went up and down again a bit. I mean, that's the resistance on the output of this one, yeah. The resistance on the output from the negative regulator just continues to climb up. Okay, I have the black lead, it's a negative rail. That one just climbs up. Yeah, this goes up then comes back down again. Right. I think the next thing I'm inclined to do, I mean, there's obviously different ways we can go about this, but I think if I get my bench power supply, set it to plus and minus 15, inject that from my bench supply, I can see how much current is being drawn on the two rails. I'm expecting to see a high current on this one. Okay, and maybe then the thermal camera might help us as well. There's an outside possibility that it's behaving this way, something to do with the way the regulator acts here when it has effectively like a lower voltage than normal coming in. I think just looking at this, there appears to be from the AC here, because there's rectifier diodes on this, the plus should go where we want it to and the minus should also go where we want it to. So let's disconnect these because it'll just read short here, little winding of the transformer. If we can do it this way, it's going to be easier because I can just put some terminals onto there, okay, spade terminals. So let's go to diode mode. Okay, and we're going to measure with a positive here to the input of the voltage regulator. Okay, and that reads like a diode. So if this end is positive, it will come through to there. If this end is positive, it will come through to there. Fair enough. So we can put the positive on whichever one we want. If this end is negative, it'll go through to there. Or this end is negative, it'll go through to there. Okay. Other way around, if positive was on here, it doesn't go there, okay, see, and if negative was on either of these, it doesn't go there. So it doesn't matter which way around we put the plus and minus, okay. The ground can go onto here, that's the same I'm sure as this point. Yeah, exactly. Or the ground could go there, doesn't matter. This is a full wave bridge rectifier. I have the schematics, we've looked at them before, but there's 1, 2 diodes there, and there's 1, 2 diodes here, which form the rectifier. So, because it's a full wave rectifier, again, it doesn't matter the polarity. So let's get that connected up. Then we don't need to power the whole thing up from the mains. We'll just power up the plus and minus 15 and see what we can see. Okay, so I've attached the ground. I have the plus and minus attached. You can just see the power supply there. Okay, they're connected here, so we're going to switch on. And we see 150 milliamps on the plus supply and 9.7 milliamps on the minus. One of the fans is running, the other one isn't. In fact, actually, let's just unplug that fan. Let's just try it again. Does it give a different reading? Okay. What do we see now? We see the same. Well, that's interesting. Okay, I'm going to look at the schematic. Okay, so this shows me something. Plus and minus 15 are here. Okay. This is the voltage regulator, which looks like it has, yes, a power transistor as part of the circuit. Okay, to boost up the current above 1 amp. Yeah. Couple of diodes in there to boost up the output to about 16 volts it shows. And then here we get 15 volts, okay, through these resistors. This is where I'm actually putting the voltage in. It should be plus and minus 28, not plus and minus 18. Okay, so we can put a higher voltage in there. That's fine. Where are those fans? Well, I'm not totally sure where the fan actually is. I can see where it connects, 12, 13. Unfortunately, this is not a searchable PDF, but it is clear that there are other voltage rails from here, so the plus and minus 15. Powered from here as well. There's another bridge rectifier here. This is a 24 volt supply. And I can also see this is saying off, slow and fast, which you might think is something to do with the fans, but I don't see the fan connectors here. Okay. Looks like this fan trigger is something to do with the LED protect light as well. There's a 5 volt supply which comes from plus VSS, which is here basically. So I'm going to put 28 volts in and let's see what it does there. One fan running again, more current on one than the other. Okay, but there's not much wattage there. 5 watts, 3 watts. So I think in fairness, I'm going to connect this back up, put my bigger current limiter in. Obviously, it looks like there's nothing going to be bad happening down with this lot. I've had the voltage in there. Possibly this is just a red herring. I haven't seen enough of these to know exactly how the current limiter lamp actually would react. Okay, so let's put the bigger current limiter on. So this one has two 72 watt lamps in, so 144 watts, okay. Where's the other one with 65? Right, so it's set to limit. We're good to go. What's it do? Well, the bulbs go out, but nothing lights up. No protect, nothing, okay. So first one was a red herring. This happens sometimes. But nothing actually came on. So power light, limit protect. Just make sure the cables are attached properly. Oh, well, as chance would have it, I actually forgot to connect these. But in a way, that's quite good. So we know there's no problem on the high voltage side because the lamps went out, basically, okay? So let's connect this. I mean, there may be a problem, but there's no short or anything like that. That's what I meant. Okay. So we connect this back up. What does it do now? Bright and dim, power on and protect on. Okay. So in actual fact, that was just a red herring, but I think we found some interesting stuff. So I'll leave all this stuff in. I mean, I could skip it, but there again, useful lessons, I think. So we'll leave that in. We're down to what the customer said. It powers up, but protect is on. Okay. And there could be a variety of reasons for this. To help us understand, I'm going to use a schematic. This sort of fault would probably be quite difficult to trace without a schematic. But I'll show you how to read the schematic and how I worked out what's basically going on. And then once we know what's going on or possibly going on, we have a chance to actually diagnose the fault, okay? So let's look at the schematic. And this is the power supply section. You can see the voltage regulators we were looking at, the various supply voltages. And the protect circuit is also on this schematic. And we can start from the most obvious place. We know the LED lights up, the protect LED. And that's the connection there to the protect LED. And that's driven through a transistor here by a signal called fan trigger. Okay, and this little arrow pointing this way, this line on these schematics tells you the direction to look to find that signal. So we know it's going up here, fan trigger. Okay, so that is what turns on the protect LED, the voltage on here. Fan trigger, you can see through this transistor, this is a comparator basically similar to the input on an op amp type circuit. Okay, there's another comparator type circuit here as well, and that is controlled here. So it says here minus 11 volts. Okay, and that is either controlled by this signal, time in, so effectively you change the voltage on the base here and you change the way this operates and it will switch this transistor on or off. Okay, as well as time in, if you look, the base also controlled via this transistor. Okay, again, this can alter the voltage on the base. And this one, triangle, this is ground, or one of the grounds. So the base is connected to ground via a resistor. And then this signal, PTC-X4, you probably figured it out because I did. PTC, positive temperature coefficient, X4, transformer. Yeah. And if we look over here, this is the transformer, and we can see there the thermistor. Okay, this is the PTC, and that's where that signal comes from, PTC X4. Okay, the other end of that PTC is connected to plus 15 volts, and being a PTC, positive temperature coefficient, this will increase in resistance as the temperature increases. So the changes in that resistance will change the voltage here. Effectively, the PTC is a voltage divider, yeah, between this point and ground because of that resistor. So we can see again, if the transformer gets to a certain temperature, it can switch this circuit and trigger this fan trigger, which puts the LED on. This circuit does a couple of other things, Luke. As well as sending that signal to the LED protect, it goes to relay drive. So this relay will be the one that disconnects the speakers if there's a fault. Yeah, disconnects the speakers. That's what you want to do if there's a fault in the amplifier. And not only that, but look, via this bit of circuit, mute drive. So it mutes the amplifiers. Yeah, mutes the input to the amplifiers. Another safety feature. So we can see what that does. Okay, we mentioned the other signal which can drive this. That's timing, and that comes from here. Okay. And you can see 1, 2, 3 op amps, a ladder of resistors forming a voltage divider, and they then drive another op amp here. Okay, so the voltage on here, and you can see it comes from here, it comes from here, it also comes from here, fan trigger, okay, via this transistor. So whatever voltage is on here will depend on either fan trigger, on whatever this transistor is doing, whatever this one's doing, and it'll set a voltage on here. And because this is a resistor ladder, yeah, as the voltage goes up or down, it will switch on the various op amps, okay, at different voltages. And look, come a bit further back, we know what fan trigger is doing. It's coming to here. You see this one, NTC 100k, yeah, another one, NTC 100k. So those are negative temperature coefficient thermistors. So as something heats up, the resistance goes down. Without looking where these physically are, I think it's fairly obvious they're on the heat sinks. So if the heat sinks get too hot, the amplifier is overheating. That will also trigger this circuit, the timing thing, if the voltage here gets enough to switch this op amp on. Otherwise, it'll do whatever these are doing. There's a lower voltages, and look what comes out here. Off, slow, fast. That's your fan control. Yeah. That goes into this little circuit. Now, if you look at the fan connections, it says CN12 and 13. Outer pins being ground and the inner one being fan plus. If you look at this, they are wired that way. You see the two outer pins? Ground, middle one is from the fan here. Okay. But this says CN2 and CN3, not CN12 and 13. I'm sure that is a misprint because look, there is no CN3. We have a CN2 or 1. Yeah. The other connections here, if you're wondering, by the way, these CN serve connections, there. So CN serve 1 pin 4, 1 pin 8, 2 pin 7. These are the test points. Like 4 fan, 2 7 temperature. So you can see those are just the test points. So we know how this works. We can see where the fans are driven. So basically, we can see that it's really the voltages here creating this time in, which triggers the whole protect circuit and does the various things. Mutes the amplifier, disconnects the speakers, puts the LED on, triggers the fans onto full. Yeah. But it's not quite so simple as that. Not quite so simple. This time in monitors a number of other things. So as well as monitoring the transformer temperature, the heatsink temperature, look, time in. This is monitoring the plus and minus 28 volt supplies. There. Okay, so if one of those supplies is missing because the fuse is blown or both, that will affect timing. Trigger protect. Okay, let's keep looking. This is one of the amplifier channels. There's 2 of them, they're identical. Timing. Yeah, what does this one do? Well, we have some transistors here, and basically this is monitoring the voltage here, which is connected, again, resistor divider, but this is the plus 82 volt rail. And not only that, if you look down here, a similar circuit, okay, this will be monitoring the minus 82 volts rail. Okay, so again, a problem with one of those voltage supplies, time in, goes into protect. And we also have another one, see, time in. What's this one doing? It's triggered by hot A, and hot A is here. So this is the output to the speaker for amplifier A, and we will have the same thing, of course, hot B for amplifier B. So what this is doing is checking for a DC offset on the speaker output. Okay, and again, if it sees something it doesn't like, it triggers timing. And I just mentioned other amplifier the same. So we've actually got from each amplifier channel 2 sources of time in. Okay, so that's 4 in total. We have a source on the 15 volt supply, so that's 5. We have the temperature of the transformer, that is 6. And we have the temperature of the heat sinks, so that is 8 possible triggers for time in. So we know that the fault can either be a problem on one of those circuits generating the time in, which is either a problem on the thing it's monitoring or a problem in the monitoring circuit itself. Okay, either of those things, those 8 sources, can generate the time in. So we have to work out whether we have an actual fault, therefore we have protect, or we have a faulty detect circuit, therefore we have protect. Another thing we can just work out from this, by the way, there's only one fan spinning. Yeah, we know that. But if you look at the circuit, both fans connect together. So there's only one control circuit. If one's spinning, the control circuit must have voltage on it. So it would seem that the only possibility for the other fan not to be working is either a faulty fan or the connections to the fan. So we have a plan there. This video is quite long now, so I think what we'll do is we'll continue this one on the next video. I'm sure some of you will probably want to replay that last bit, how I went through that circuit. It's quite interesting, I think, because what we have here is all analog circuitry. Yeah, not only is there no microcontroller, there isn't even any logic. Yeah, it's all done with analog circuitry, and yet it controls the system, you can see. Yeah, so let me know what you think down there about that. We'll carry on with this repair on the next video, and I look forward to seeing you all soon on Electronics Repair. Ciao for now, guys.